When you use the adjective molar in front of any word, then that means per mole. Like molar mass is grams per mole, mass per mole. So when we say molar volume, we mean the volume per mole. So volume of 1 mole of gas particles would be the molar volume of a gas. So to calculate the molar volume, you simply divide the volume by the number of moles. Okay, and so the unit for that would be liters, a unit for volume, divided by the unit for mole, which is mole. Okay, so liters per mole. Now, let's go back to our ideal gas equation, and let's see if we can determine the molar volume by rearranging this equation. If we divide both sides by n, okay, and p, and p, then your p cancels out from the left side, so on the right side, and n cancels from the right side, so you can see that V over N, the molar volume, is just equal to RT over P. Now, an important consequence of this is this. If you're dealing with a gas sample at a given pressure, constant temperature, so a given temperature and pressure, okay, then V over N will be a constant. What does that mean? When the ratio of two quantities is a constant, then we say the two quantities are directly proportional to each other. So we say volume is directly proportional to N. This symbol, by the way, this looks like alpha. That means directly proportional to. So what that means is volume is equal to some constant times N, okay, at a given temperature and pressure. Or we can say, if we rearrange this, you can see that V over N is equal to that constant, and that constant happens to be RT over P. Okay? So that's called your proportionality constant. So if V is directly proportional to N, what does it mean? That means you have more moles of gas. You expect it to occupy a bigger volume at a given temperature and pressure. So in a way, you can use volume as a way of determining how many moles you have, provided you know what the temperature and pressure is. Okay? Smaller moles of gas, smaller volume. Okay? So at a given temperature and pressure, we say then that the molar volume, V over N, is a constant. So you can also say V over N1, V1 over N1 equals V2 over N2. Okay, so if there is a change of moles of gas from N1 to N2, okay, then the volume will change from V1 to V2. Okay, and if you know V1, you can figure out V2, provided that the pressure and temperature is the same in the two circumstances. Okay, so another way of saying that molar volume is another consequence of this is to say that if you have equal volumes of gas at the same temperature and pressure, then they have to have equal number of particles. So if V1 is equal to V2, right here, if V1 and V2 are the same, then N1 must be the same as N2, provided, like I said, that your gas samples are at the same temperature. All right. Another way of expressing this idea is to say that at same temperature and pressure, all gases will have the same molar volume. Okay? Molar volume would be equal to RT over P. So RT over P is the molar volume of an ideal gas. At STP, in fact, that value we've seen earlier is equal to 22.4 liters per mole. The molar volume of a gas at STP is 22.4 liters per mole. So all of these statements over here, equal volumes of gas have equal numbers of particles, same temperature and pressure, all gases have the same molar volume. Volume is directly proportional to N at a given temperature and pressure. Those are all statements of what we know as Avogadro's law. Okay? And you may see it referred to as Avogadro's hypothesis in some textbooks. And historically, it started out as hypothesis. So let's look at this example, application of Avogadro's law. Which of the following gas samples contains the most gas particles at the same temperature and pressure? 2 liters of CH4, 1 liter of H2, 2 liters of helium, or 4 liters of helium? Well, that would be the biggest volume, right? Volume is directly proportional to number of moles at a given temperature and pressure. In fact, you can say N equals PV over RT. Another way of looking at it, at the same pressure and temperature, the bigger the volume, the bigger the more moles you have. Or you can rearrange this. Volume equals nRT over P. Okay. Then you can say the more moles you have, the bigger the volume. Okay. Number of moles here times molar volume. You can see this RT over P is volume per mole. Okay. Times the number of moles will give you the actual volume. Let's take a look at this other example right here. Which of the following gas samples contains the most number of atoms at the same temperature? Okay, and so the way to do this is you just say N, number of particles, is equal to PV over RT, right? Okay, so same temperature and pressure, so this quantity right here is the same. P over RT is constant, so the bigger the volume, the more moles you have, right, of particles. But then you have to multiply that by the number of atoms per molecule to get the actual number of atoms. So how are we going to do this? So let's say sample A would be, okay, your N is equal to P over RT times V, okay, or V is 2 liters, right? So let's just going to say 2 liters there, times 4 atoms, oops, sorry, not 4 atoms, 5 atoms per molecule, right? 5 moles of atoms per mole of molecules. So that gives you 10P over RT, you might say. Okay, let's just call P over RT as X. So that's going to be 10X. Let's try H2. H2, number of moles is P over RT, PV over RT. Our volume is 1. Okay, so times 2 moles of H in 1 mole of H2. Since this N, this is N moles of H2, right? That's the N from the ideal gas equation. So this is just N of H, number of atoms of H. So that gives you 2X, right? The next one, helium, number of atoms of helium is P times 2 liters over RT. So that's just times, well, helium is already an atom, so this is going to be X. Okay, and then finally the last one, moles of helium for the sample D would be P times 4. I'm sorry, this is 2X. Okay, and this is P times 4 over RT. So this is going to be 4X. So you're comparing 4X versus 2X versus 2X versus 10X. So CH4 would have the most number of molecules. Okay? Most number of atoms. Now it doesn't matter what the temperature and pressure is, since we're comparing all of them at the same temperature and pressure.